Hello everyone, today the theme I'm sharing with you is reliability requirements and solutions of offshore PV systems. Briefly, my presentation is in 5 main sections. First, I will provide a general introduction of offshore PV market and policy. According to the report from International Renewable Energy Agency, the FPV market has spread globally with more than 60 countries pursuing future deployment of FPV plants. Of these, 35 countries are already harboring 338 FPV power plants. Table 2 provides a summary of some of the planned FPV projects globally in the coming years. According to a previous study, the global FPV market is expected to maintain its growing trend with a growth rate of 30% until 2024. A variety of forecasts estimate the market potential to accommodate between 4 GW and 10 GW of installed FPV capacity over the next 5 years. In the Chinese market, the development of most of offshore PV projects is still in the technical exploration, and the experience is insufficient. Most of the large-scale projects that have been finished are built along the coastal mudflat. However, based on the macro incentive project policies of the Shandong government in China, many offshore demonstration projects have been implemented in Shandong in 2022. The coastal environment in China is harsh with strong wind and waves. Considering project safety, pile-based PV systems are certainly the mainstream in the market of the offshore PV systems. Based on the area of Chinese coastal line and coastal mudflat area, here we have estimated the exploratable area and installed capacity of pile-based offshore PV. As shown in the red table, the pile-based coastal PV is expected to be about 180 GW, and the mudflat PV is expected to be more than 210 GW. Then we will discuss with characteristics of marine environments. The marine environments can be divided into 5 major areas based on its corrosion impact and height, namely the marine atmospheric zone, splash, tidal, submerged, and subsoil. The area at the height of more than 2 meters from the sea level is the atmospheric zone with higher temperature and humidity. The corrosion rate of offshore is more than 4 to 5 times higher than inland. Similarly, the influence of winds and UV radiation rate are also more severe. The splash zone is located at a distance of 0 to 2 meters from sea level, where modules are often impacted by waves. The surface alternates between dry and wet conditions with sufficient water and oxygen supply, make it the most severely crowded area in the marine environment. The tidal zone is located between the mean high water line and the mean low water line, which is protected as a cathode area of oxygen concentration cell and has a low corrosion rate. However, there is a risk of marine biofueling in this area. Therefore, the floating bodies of floating PV systems are often attached to various marine organisms, causing weight increase and sinking, and finally, the modules soaking in water. In the end, regarding submerged zone and subsoil zone, the anchor system and pile foundations in these 2 zones, rather than our modules, have to face corrosion issues. Therefore, PV modules suffer from relatively harsh environments such as high humidity, south breeze, strong wind. This causes various challenges to PV modules, as shown in these pictures, like accelerating age of connectors, module frames, destruction of module structures, and marine organism attachment. To face with this harsh environment, a series of tests should be complete to ensure the reliability requirements for modules in marine environments. All these results conducted by PV Node fully verify the high reliability of our Jinko's N-type, which has lower LID and LETID than PERC. In accelerated aging tests like UV 90 kWh, thermal cycle, damp heat, and mechanical stress sequence, our N-type modules satisfy the 5% degradation of IEC standard requirements and demonstrated the superior performance. In order to adapt to the marine environment, the modules also need to meet targeted testing requirements. Alternating salt spray, saltwater pressure immersion tests are conducted for strong corrosion environments. Thermal cycle 392 cycles at 110 Celsius degree is conducted for frequent temperature changes. UV plus damp heat in 1000 hours accelerated AG test is conducted for the long-term UV and humidity, causing the efficacy loss of module structures such as glass frames. 1000 par, 1000 cycles, the dynamic mechanical load at 65 to 85 Celsius degree and wind tunnel testing are conducted to evaluate the mechanical property and wind resistance of our modules. Hotspot testing without cleaning after salt spray is conducted to evaluate the hotspot resistance of modules because there are some difficulties in cleaning and maintenance for offshore PV modules. Therefore, the optimization of module materials is the ultimate guarantee for achieving safe, reliable, and continuous operation for our offshore PV project. So for the marine environment, we have optimized the module materials in many aspects, mainly in 6 points as shown. The first point, applying anodized aluminum 20 micrometer frame compared with 10 micrometer of conventional module frame. This helps to reduce salt water and salt spray. The second point, apply double layer coated glasses. Compared with single layer of conventional module, this helps to ensure both higher light transmission and anti-humidity. The third point, adopting POE rather than EVA to ensure lower vapor penetration, better thermal stability, and high temperature endurance, while also mitigating potentially induced degradation. The fourth point, apply more silicon sealant around the edge of the solar cells and junction box to improve the cohesiveness, which ensuring that electrical connections are protected from humidity. The fifth point, compared with potential P-type PERC cells, N-type top contact technology has high efficiency and lower degradation, which can bring more power generation. The sixth point, applying additional double protect of IP68 connector, which places fluoro rubber protective sleeve and string tube to deliver better waterproof and anti-corrosion capabilities. On the one hand, frames encapsulant glass connectors are optimized to figure with the reliability issues. On the other hand, TOPCon N-type cells bring profit to offshore PV project inverters. Investors, because of the high SUF, higher foundation, floats, and the brackets, the advantage of adopting N-type have been amplified, which help to save project cost and increase revenues. Specifically for this stimulated floating PV area, the number of modules can be saved by more than 400 pieces. Meanwhile, the land cost can be saved by 5.2%. The estimated BOS cost can be saved by more than 5 cents per watt. The electricity generation in this case can increase by 3.7% throughout the life cycle. Then take a quick look at a demonstration project. We provide 200 kilowatt solar PV modules for CMIC vessels. This was first groundbreaking venture combines N-type TOPCon technology with domestically manufactured offshore semi-submersible floating solar PV system. The platform has Chinese independent IP rights and marks a significant milestone in the exploration and practical application of marine-based PV projects. In the end, let us discuss with offshore PV system solutions. There are 3 main types of offshore solar power plants based on their design. Fixed pile based type is suitable for coastal area where the sea depths had better be lower than 5 meters, and typically the installation method of modules is same as the inland modules. Floating platform type is suitable for sea area with a water depth of more than 5 meters. Floating thin film type is a mainstream product of the Norwegian company, Ocean Sun, and this special type requires special installation and custom design. In detail, fixed pile-based PV systems have different structural forms. Bracket support plus piles is the conventional scheme. Through applying long-span steel platform, we can save the numbers of the pile foundations and reduce the corrosion and water intrusion risk on modules. Flexible structure plus its piles structure solution has reasonable structural stress but higher cost and without any application. And honeycomb structure has fewer pile foundation, but the structure is complex, causing difficulties in construction. Typically, floating solar plants consist of solar panels mounted on floating platforms. The platforms can be divided into three types: floating tube, floating box, and buoyancy ring, floating seam membrane. At present, most of the floating tubes and boxes are made from HDPE, which means high-density polyethylene, while floating seam membrane has not widely used in domestic floating PV projects. As previously mentioned in the second chapter, strong wind, especially typhoon, would threaten PV modules. As shown in the picture, floating PV projects capsized, some modules fell from the fixed bracket, some hot hoops of flexible PV support slipped. Therefore, we need to take some measures to cope with these issues. Reducing tilt angles can reduce withwall area and the wind pressure withstood. Reinforced connected points like 6-point installation or clamps for double flat fixation rather than conventional 4-point installation, which can enhance the load capacity of modules. Certainly, it's necessary to conduct inspection and troubleshooting before a typhoon arrives. Similarly, wave dispersion method can provide a protect area for a floating PV project to remove the wave height and energy. Rubble mount breakwater and permeable breakwater are normally used in some harbors. Floating breakwater is a relatively innovation and flexible method to filter the wave disturbance. After simulation, wind tunnel test, and a pilot test conducted by some floating system companies, it has been verified that breakwaters are necessary for floating PV systems. Bird dropping are more severe in coastal and marine areas. The following are various bird deterrent methods. For example, laser bird deterrent device can create a visual stimulation to scare away birds. Marine biofueling is also an environment factor affecting floating offshore PV systems. Usually, it includes the following simplified steps within 1 month from the beginning to the end. Namely, the stage of condition film, bacterial biofilm, microfilling spores, and macro fouling in the last. Physical anti-fouling methods can be commonly divided into 3 categories. Mechanical cleaning is a mature technology, but efficiency is low. Ultrasonic cleaning has high efficiency, but may accelerate corrosion. UV inactivation is safe and stable, but can be absorbed by organic compound. About chemical anti-fouling methods, biocides are effective but have environment risks. Electrolytic method is easy to operate but has higher cost. Anti-fouling coating can be divided into SPC type and FRC type. SPC has been extensively applied but harmful to the environment, while FRC is environmentally friendly but expensive. Thank you, and if you need clarification on any point, you are welcome to send me email.